Welcome to part 3 of this week's online lecture. In part 3 we will continue our discussion of rigid diatomic molecules. I want to briefly summarise some of the important points from part 2 before continuing our discussion of diatomic molecules. First, I want you to appreciate how we came up with the energies for the quantum states. No matter which spectroscopy we discuss, the process will be the same. We will be solving the Schrödinger equation. The first thing we will do is identify the Hamiltonian. This is determined by the system. For the rotational system, there is the rotational kinetic energy operator, and that's it. The potential energy is zero, just like the particle in the box. With the Hamiltonian identified, we simply solve the Schrödinger equation. The solutions are all well known in mathematics, so this is just a matter of looking up the general solutions. With the general solution, we apply the boundary conditions for the particular problem, and this results in quantization. We can then operate on the wave function with the Hamiltonian to identify the energies as a function of the quantum number. How did this all work out for our rotational system? Well, we looked at the simplest of molecules, that is the diatomic. We also assumed that the bond was rigid. We will relax this approximation at the end of the lecture. When we solve the Schrödinger equation, then this is the solution of the energies of the rotational levels. It is equal to the rotational constant times j into j plus 1. So when j equals 0, the energy is equal to 0. If j equals 1, it is 2b. If j equals 2, it is 6b. And this symbol F is the rotational energy term. This is the energy expressed in wave numbers. So the B here is in terms of wave numbers as well. In spectroscopy, we have light interacting with matter. In order to interact, the incoming photon energy, h nu, must match the energy difference between two rotational states. Well, the energy difference between j equals 1 and j equals 0 is 2b minus 0 equals 2b. The energy difference between levels j equals 2 and j equals 1 is 6b minus 2b is equal to 4b. Rotational energy is quantized. This quantization came about because of the boundary condition that the wave function must be single-valued as our reduced mass particle circumvented the origin and returned to its original position. So that's why the energies of our system are indeed quantized, and we get our J quantum number. The other thing we can do with quantum mechanics is determine the selection rules. This is because the selection rules come from the transition moment, and the transition moment depends on the wave functions for the system. So for the rotational system, there is the gross selection rule, which is that our system must have a permanent dipole moment. Mu is the symbol for dipole moment. If the molecule has a microwave spectrum, then it must be non-zero. When we cover group theory, we will see why molecules of certain symmetry have microwave spectra and others do not. We will also do exactly the same when it comes to vibrational spectroscopy. The second selection rule, which again comes from consideration of the transition moment, is that delta J is equal to plus or minus 1. Delta J is the final rotational quantum number minus the initial quantum number. The selection rule requires that this can only change by 1, so I can go from j equals 2 to j equals 3, and I can go from j equals 3 to j equals 4, but I cannot go from j equals 2 to j equals 4. Remember that we did manage to justify this semi-classically by conserving angular momentum in our photoreaction, and noting that the photon has 1 unit of angular momentum. The angular momentum of a photon can be plus 1 or minus 1. So therefore, if I'm going to conserve angular momentum, the angular momentum I have in the reactants, i.e. the angular momentum of the J state plus the angular momentum of the photon, must be the same as the angular momentum of the system after the photon has been absorbed. And so the angular momentum can go up to J plus 1 or down to j minus 1. It cannot stay at the same j level, and it cannot go up to j plus 2 or j plus 3, where j in this is the initial quantum number. So this is the picture we ended up with, and these transitions in red here are where we get changes of j of plus 1 and are thus all allowed. And these transitions, which have been crossed out, are where j is changing by 2 or 3 respectively and are not allowed. This leads to our spectrum. The transition from j equals 0 to 1 will occur when the system absorbs a photon with energy 2b. Associated with this is the spectral line at 2b. The transition from j equals 1 to 2 happens when the system absorbs a photon with energy 4b. Associated with this is the spectral line at 4b. The next transition from j equals 2 to j equals 3 will occur at 6b. Each of these lines are separated by 2b, and this explains the equidistant separation of lines in a rotational spectrum. So what is the use of doing this? Well, I have a model which expresses the energy of each of the spectral lines in terms of the rotational constant. Once I've got the rotational constant, which I can get by simply dividing the frequency difference by 2, I can calculate the moment of inertia, because the rotational constant is inversely proportional to the moment of inertia. And once I've got the moment of inertia, I can use that to determine the bond length of my molecule, if I know what the reduced mass is. Or perhaps, if I've got a spectrum of more than one isotope, I can determine the isotopic abundance of the various elements. In last week's online lecture, I mentioned degeneracy, and I've mentioned that it is going to be important. And in particular, I've mentioned that the degeneracy will be important in terms of the intensity of each of the spectral lines. Remember that the intensity is dependent on the Boltzmann distribution, and the Boltzmann distribution, of course, depends on the energy gap, but it also depends on the degeneracy of the individual energy levels. So we need to work out what the degeneracy is for each of our levels. So let's go back to the solution of the Schrödinger equation for my rotational system. This was the result of solving the Schrödinger equation. The energy of the rotational level J is equal to J into J plus 1 times h bar squared all over 2I. We can relate our rotational energy E sub j to my angular momentum, which I have given here as J. It's a bold J because it's a vector, and I can write down my rotational energy simply as the angular momentum squared divided by 2I. This is analogous to linear kinetic energy being equal to the linear momentum squared divided by 2m. Remember that angular momentum is the moment of inertia times the angular velocity. So the angular momentum squared would be I squared omega squared. If I divide it through by 2I, it will be equal to a half I omega squared. So we can more easily appreciate the analogy between a half I omega squared for rotational kinetic energy and a half mv squared for linear kinetic energy. Angular velocity is the analogue of the linear velocity, and the moment of inertia is the analogue of mass. Now that I know that my energy is equal to j squared over 2I, I can compare this to my rotational energy that I determined from the Schrödinger equation. And we can see that my angular momentum is equal to the square root of j into j plus 1 times h bar. So this is the magnitude of my vector, but it also has direction. So in this particular case, it is telling me, as it is pointed upwards, that my molecule is rotating in an anti-clockwise direction. So if you know where the vector is pointing, you can use the right hand rule, where the thumb points in the direction of the vector, then my fingers determine the direction in which my molecule is rotating. If the vector is pointing downwards, then my fingers point in a clockwise direction, which means my molecule is rotating in a clockwise direction. So there are two directions in this particular case with reference to the axis of rotation. It could be rotating clockwise or anti-clockwise, depending on whether my angular momentum is pointing upwards or downwards along the axis of rotation. I need to discuss the orientation of the angular momentum vector in space. So far, quantum mechanics has told me the magnitude of the vector, but I want to know the direction. So I've got the z-axis that can be defined however you want. It's an arbitrary axis. I'm going to project my angular momentum vector onto this arbitrary axis in order to tell me something about the orientation of the rotational motion. So I'm going to project my vector onto my reference axis z. If this is my z-axis or laboratory axis in blue, and this is my rotational axis in red, and here is my angular momentum vector, just project it so that this angle here is 90 degrees. So I've created a right-angled triangle where the j vector is the hypotenuse, and the projection of the vector will have a magnitude j sub z. Depending on how the molecule is oriented, the value of z can vary anywhere from the actual magnitude of the angular momentum in the positive direction to the magnitude in the negative direction if I rotate it all the way round. But this is not going to be the case. In fact, it isn't arbitrary. My molecule can orientate itself with respect to my laboratory axis in only certain directions. The orientation is also quantized. This is, I agree, a bit tricky to appreciate. My value of j sub z here can only vary from plus j to minus j. So what that tells me is that my vector can never be perfectly aligned along the z-axis, because the magnitude of my j vector is the square root of j into j plus 1 times h bar, and my jz can only have an absolute magnitude of j h bar, whereas j can have a magnitude of the square root of j into j plus 1 times h bar, so it is always slightly larger. The value of jz is quantized. Notice how many orientations there are for a particular value of j. For instance, if I'm in the j equals 2 rotational level, then there are only 5 spatial orientations that my molecule can be in. It can be in m sub j equals 2, m sub j equals 1, mj equals 0, mj equals minus 1, and mj equals minus 2. If I'm in the j equals 1 level, there's only 3 possible spatial orientations. If j is equal to 3, there are 7 possible spatial orientations, and if j is equal to 4, there are 9 possible spatial orientations. You can probably think of an analogue you've already come across. How many s orbitals do you have in a particular state? You have 1. How many p orbitals do you have? 3. How many d orbitals do you have? 5. How many f orbitals do you have? 7. And it is for exactly the same reason. Remember, you've got your L quantum number, which for s is 0, for p is 1, and d is 2. And you have your m sub L quantum number, which can only have integer values from L to minus L. The maths underpinning this is identical to that for rotational motion. This m sub j quantum number is also quantized because of a boundary condition that must be satisfied, and it is exactly the same type of boundary condition that leads to the m sub L quantum numbers in atomic orbitals. The reason why we've got 2 quantum numbers in this problem, that is the j quantum number and the mj quantum number, is that in order to define the position of a particle in a sphere, which is the model that we're using here, we need 2 coordinates, theta and phi, the latitude and longitude. There is a boundary condition associated with each of these coordinates, and so there is a quantum number associated with each of these boundary conditions. You always have the same number of quantum numbers as you have coordinates, because there is a boundary condition to be satisfied with each coordinate. So when we look at vibrations and electronic spectra, we will see how that gets more and more complicated. So we've come up with this idea of spatial orientation before, and you also can appreciate that p orbitals for hydrogen atom at least have exactly the same energy, that they're degenerate. You can see that it doesn't matter which p orbital the electron is in, it has the same energy because they are identical to one another. It starts to get a little more complicated to appreciate that the d orbitals are all identical to each other. For the p orbital you can see it's just a matter of rotation, but for the others it is not so obvious. The dz squared orbital doesn't look particularly like the dxy orbital, for instance, and yet you know that they have the same energy if we have a single electron system. The reason you can't tell that they have the same energy is because you're a three-dimensional being. If you were a five-dimensional being, then they would look identical to one another, but perhaps that's a little too abstract. This issue of spatial degeneracy does take some getting used to. On this slide you can see two representations of this spatial degeneracy. On the left you can see the j vector being projected onto the z-axis. J equals 2, and so there are 5 possible mj values from +2 to -2. On the right you can see 5 cones being swept out to represent the angular momentum vector. These cones are meant to remind you that the angular momentum vector can lie anywhere on the surface of one of these cones for a particular value of mj. You don't know where on the cone, as you only know the projection onto the z-axis. It does make sense that the rotational energy depends on j, but not on mj. It should not matter what the orientation of the rotational axis is with respect to the laboratory. There is nothing about space which makes a particular direction more important than another. The importance of this spatial orientation is that it leads to degeneracy. If my molecule is in the j quantum state, then there are 2j plus 1 possible orientations which all have the same energy, the definition of degeneracy. Let's look at this degeneracy in more detail. Because the molecule can be in these 5 different orientations when in the j quantum state, it means that we have 5 energy levels, and all those 5 energy levels have the same energy. So they are all degenerate. So this is where degeneracy is coming from. Although this quantization of spatial orientation has not changed the energy of the system, it is still a separate energy level. So my j equals 0 level is not degenerate, there is only one energy level. My j equals 1 level will have 3 energy levels of exactly the same energy. My j equals 2 level will have 5 energy levels of the same energy. My j equals 3 level will have 7 energy levels of the same energy, and so on. So the number of energy levels with the same energy is increasing, and you can work it out. The number of degenerate energy levels for any value of j is equal to 2j plus 1. Here are my energy levels again. But I know that in fact the degeneracy, given the symbol g, for j equals 0 is g sub 0 is equal to 1. When j equals 0, mj is equal to 1, 0 or minus 1, and so the degeneracy of this level, j sub 1, is equal to 3. When j equals 2, there are 5 levels. When j equals 3, there are 7 levels, and so on. In general, the degeneracy of the jth state, g sub j, is equal to 2j plus 1. So let's reinforce that again and summarize what I've tried to illustrate so far. So my rotational energy, E sub j, is quantized because of boundary conditions for a particle moving on a sphere. If we solve the Schrödinger equation, we'll come up with this formula, and the boundary conditions mean that it is quantized so that j can only have values of 0, 1, 2, 3, etc. The angular momentum we can determine to be is equal to the square root of j into j plus 1 times h bar, and again it is quantized. It depends on the j quantum number. But the component of the angular momentum j on an arbitrary axis z, j sub z, is also quantized. This is the spatial orientation arising from a boundary condition of the second coordinate for my particle moving on a sphere, and so j sub z is equal to m sub j times h bar. The mj is my new quantum number, and mj can have values of 0, plus or minus 1, plus or minus 2, all the way up to plus or minus j. It is limited by the rotational level that you are in, and that leads to my degeneracy of 2j plus 1. Surprising though it may seem, my rotating body cannot point in any arbitrary direction. Its orientation is determined by quantum mechanics. If I set myself rotating, I can rotate apparently in any direction because my rotational quantum number is huge. The difference in rotational energy level to the next is minute. You cannot feel the discontinuity. Similarly, you cannot feel the quantization in spatial orientation because the difference in angle is minute. You can't see quantization by looking at macroscopic objects. You can only see this at the quantum level, which is the reason why it appears so weird, because we never experience it. There is a selection rule associated with MJ as well, and that is that the change in MJ, delta MJ, must be equal to 0 or plus or minus 1. However, as the rotational energy does not depend on the MJ quantum number, this selection rule has no effect on the spectrum. When could we have an exception? We can have an exception if my molecule is not in an isotopically even spatial environment, if there is a direction applied, if my molecule knows what the z-axis is. But how can I let my molecule know what the z-axis is? I can do it by applying an electric or magnetic field in a particular direction. If I apply an electric field in a particular direction, there's going to be an interaction between my dipole moment in the molecule and the external electric field, and the interaction now does depend on the spatial orientation, and so the energy of the system will depend on the MJ quantum number, and the selection rule with regard to MJ will affect the rotational spectrum. The lifting of the degeneracy can be seen in a special effect known as the Stark effect. Say that I was in the j equals 7 level. Therefore I could have 2j plus 1 levels, 15 possible levels, which will be degenerate if there is no electric field applied. As soon as I apply an electric field, however, the energy levels are split, and if mj is equal to plus or minus 7, the energy level will be down here. If it's equal to plus or minus 6, it will be here, and so on, with mj is equal to 0 up here. So we've lifted the degeneracy. And now, the fact that delta mj is equal to 0 or plus or minus 1 becomes kind of important. One of the reasons why this is useful is that the energy of my level now depends on both my j level and the mj level. So the rotational energy is equal to b times j into j plus 1, as before, plus now we've got this additional term. And this additional term depends on the electric field, xi, and also depends on the dipole moment, mu, with this additional parameter a, which is given by this expression, which you can see depends on the j and mj quantum numbers. Because this energy here depends on the electric field and the dipole moment of the molecule, this is quite a useful effect in order to measure the dipole moment of the molecule. So again, that is the reason why we do spectroscopy, not to create a pretty spectrum, but to use the spectra to determine something about the molecule, whether it is the bond length or bond angle. But in this case we can use the Stark effect to determine its dipole moment, and we can do so quite accurately. So what about the intensities of the rotational lines? Remember, we spoke about this in our general discussion of spectroscopy, that the spectral line intensity is controlled by both the transition probability, and the population of the initial state. And the degeneracy that we've just been looking at is going to affect the population of the initial state. If you've got more levels of a particular energy, the molecule has more choices of where to go, and so therefore you'll get more molecules in those levels. It is kind of an entropy effect that is going on here. The more that your level is degenerate, the more molecules you will find in that level. So it doesn't just depend on how high the energy is above the reference energy. It also depends on how many levels there are at that particular energy. If we actually do the quantum mechanics and calculate the transition probability for a rotational system, that transitional probability is pretty much the same for all transitions. You would not notice any effect unless you were doing some really high quality spectroscopy. So we can largely ignore the quantum mechanical effect here of changing transition probability. However, the population of the states changes dramatically. This is the Boltzmann distribution law. This expression relates the number of molecules in the N state compared to those of the molecules in the M state. This ratio depends on the ratio of the degeneracies in those two states. So if the N state is more degenerate than the M state, there are going to be more molecules in the N state. To complete the expression, the ratio of the degeneracy is multiplied with the exponential of minus delta E over kT, where delta E is the difference in energy between the N state and the M state, and kT is the amount of thermal energy available to excite molecules into any excited state. So let's have a look at how the degeneracy is going to change the population distribution. It frequently makes sense to reference the population to the ground state, the J equals 0 state. That is, make the ground state our reference state. This makes our distribution somewhat simpler because the J equals 0 level is not degenerate, so the degeneracy in the denominator disappears. Remember, the degeneracy of any level is equal to 2J plus 1. So therefore the ratio between N sub J, the number of molecules in the J state, to N sub 0, the number of molecules in my ground state, is going to be equal to 2J plus 1 times the exponential of minus the difference in energy, which is the energy of the excited state, because the energy of the ground state J equals 0 is 0, over kT. So this is my expression. So I've got two terms to consider. I can see that as J increases, this 2J plus 1 term, the degeneracy, is increasing. But as J increases, this exponential term decreases because of the negative sign. So I have two competing effects as J increases. The degeneracy means that I should expect more molecules in higher J levels, but the exponential term is telling me that I should see fewer molecules as J increases. So how does this pan out? Well, I'm going to get a balance between these two terms at some value of J. There will be a maximum. And you can appreciate this by doing some simple calculus. I can simply differentiate this expression with respect to J. When the expression is a maximum, this gradient is equal to 0. The differential is not too tricky. And if you solve this, we can find the maximum J value. And the maximum J value is approximately equal to this expression on the right. The fact is that when we differentiate it, we are assuming that J is continuous, but we know that that is not true, as J is always an integer. So that means there's going to be a bit of an issue with regards to this. So when I set it equal to 0, the J max that I will come up with is a non-integer. It's got to be an integer, so we've got to decide which it should be. I could simply substitute this expression and find out which it would be, but why bother? What is important about this? The fact is that it depends on temperature. If I know what the rotational constant is, I can get that from the space between my spectral lines. Identifying which spectral line has the greatest intensity, which is the J max line, I can use this information to determine the temperature at which the molecule is emitting or absorbing radiation. I can determine the temperature of my sample. In the laboratory, that is not a particularly useful thing because it would be a lot easier to measure the temperature using a thermometer. But what if the molecule is in the atmosphere or even further away in space? Information from the intensities of the spectral lines can be used to determine the temperature. But let's have a closer look at the effect on intensities. What will the spectrum look like? And it will look a bit like this. In this spectrum we can identify Jmax, the most intense line. The first line is the transition from 0 to 1, the next from 1 to 2, and the most intense line is from 2 to 3. So Jmax is equal to 2. If I substitute it into this expression, I can calculate what the temperature is. This is the end of part 3 of this week's online lecture. Please continue on to part 4.